We'll see.
Well, no, actually, no.
I know. Well, you know, a problem. I know, but I mean.
Oh, also,
Mhm.
shaming. Carrie left her credentials saved on one of the computers upstairs.
Her credentials page?
Yeah, you know how Safari asks to save your.
Oh, so into her Gmail or something?
So she saved it for her school account
Oh, well, you might want to let her know.
campus.
Yeah, that's yeah, that's a very common way that people get hacked. They leave themselves logged into a machine or something like that.
You know, not only is it logged in, but it's saved for future use.
Yeah, yeah. Well, I'd better let her know. It's an easy mistake to make. Anyway, so let's see. Let's go here. All right. So this is 141, and we're very near the end of the semester, of course. All right. Looks like my network is not very good. CCSF guest. Let's try staff. See if staff is any better. All right. Now, it could be somebody hacked me, but the most likely suspects, I guess not. Okay, anyway. All right. Hey, so, all right. So we're down here at Elliptic Curves, and after this, there's just 2 more classes, TLS and Quantum. So that'll be it. Then there's a final exam online for a week. There are a lot of guest speakers and such coming. We had one last night. This guy was very interesting with his Linux on Windows.
Nice way of putting it.
What's that?
That was a nice way of putting it.
Well, I thought I thought it was kind of nuts, but he presented his position. I'd like to see. It was a product and he seems to be actually succeeding, making money out of it. So it's anyway. I was interested to hear it. So we have Aumasson coming tomorrow, and then I think there might be another one. No, I guess maybe he's the last one. All right. Anyway, all right. Then we're all off to, and there'll be another Purple Team competition on Saturday, and on the 11th we'll be doing it in San Jose. All right. So I guess that's enough schedule. Let me take a look at the news. I know there's been a lot of exciting news. YouTube took down one of my videos, but they haven't taken down any more. They said if they found more hacking videos in my channel, they would ban me completely. And I said, well, I'm host then, but apparently none of the rest of them are considered offensive. So that's fine. Yeah, that's interesting. That's actually quite interesting. And well, I'll just mention a few of these. This one I thought was very interesting. This is the second time, or maybe the third time in the last couple months, Bloomberg has done the same thing. They made up a completely fake story claiming that the Chinese had backdoored something when they totally didn't. They claimed it was a secret backdoor and it was just a telnet service that runs on the local area network, which every router has for a long time. And they claimed it was a deliberate spying backdoor. They also claimed that the Chinese were putting special secret hardware chips in their devices to spy on people, and it was all totally false. And when they published that, and it hit the front page everywhere, and then they found out it was totally false, they claimed Apple and Google were buying this stuff and it had secret Chinese chips in it, and everybody said, they totally don't, it's not in there, and they didn't admit they were wrong. They stuck to their guns, then they claimed they were having an investigation. They never published the results of the investigation. So I think Bloomberg wants to be president, and he seems to be on track to get there this way. This is apparently how presidents get in now, about just bald-facedly lying and just lying more every time they catch you lying. But it's just spectacularly unreliable as a news source for technology. People seem to still respect it for economic news or something, but I don't know any news source at all like this that just publishes absolutely fake stories. They're proven beyond a shadow of a doubt to be fake, and they just keep on publishing them and claiming they're true. And somehow people still treat them as a news source. Anyway, yeah.
Go back.
All right.
Scroll down. Scroll up. Are we there? How does Mrs. Gates got billed to drive the kids to school?
I have no idea.
That looks very interesting.
A book on gender inequality. So she made negotiations to get billed to drive her daughter to school. Huh. Unpaid labor, yeah, the chip, yeah. I don't know if she tells us how she did it. Nope. It wasn't obvious how she did it, but she certainly did. That's, of course, a big issue. This one I thought was very interesting, especially since it pushes an agenda I don't like. But this is an interesting counter. These are the people who want to censor the web. And this is an interesting story. There was a PBS or a TV special about a teenager that committed suicide, and they won awards for this fantastically accurate depiction of this person explaining why they committed suicide. And a whole bunch of teenagers did commit suicide after watching this because it was so effective at expressing how they feel. They have like 13 videos this kid recorded of why he was going to kill himself. Then he killed himself. They said, wow, that's great. That's so real. And this is what all the people who want to censor the internet say. You got to take off this stuff because people will do stupid things when you put stupid things on the internet. And unfortunately, there may be some truth to it. I don't like it, but that's the way it is. Anyway, this I saw a couple of years ago. It's come back again. If you get an old insulin pump with a vulnerability, you can then use it to make a superior delivery of insulin by breaking all the rules and doing unapproved hacking to make a custom device that is not the way the manufacturers make it for some reason. And there's a huge demand for these old devices. This is old hat for hacker circles. People always want old Wi-Fi cards and old hardware of various types that are easier to hack. This would be kind of fun if I can set it up. There's something called a Confluent server, and it's got a past traversal vulnerability. This sounds kind of like Drupal-geddon. I'm thinking it'd be fun to do. And this guy found you got a Google dork for it and a simple attack, and he found bunches of them online. You can totally exploit them. And so he dumps out it looks really simple. You can load a template. This is like an XML external entity injection. You can load a template, and the template is loaded from a URL, and you can point the URL to the wrong place. So you can do local loading of the password file. And I think you can also inject code from external places. So he found Google dorks to find them, this pattern in the URL, and he found thousands of them he can exploit. So it might be worth setting up one of these. This is another thing that would also be awesome. Everyone's getting upset about a single line in the Mueller report that suggests that not only did the Russians scan election machines and try to get in, they actually did get the ability to alter the votes on some election machines, which may or may not be true. But in any case, one thing they said, which I thought was very interesting, is that all the election machines are currently protected by these Albert sensors, which are the US government standard piece of hardware. And it's apparently something like a web application firewall. And apparently this is the normal thing. It's been around for a while, and there are various people saying these things aren't very secure. And I'm thinking, well, you got to get one of them and play with it and see what they're like. And hopefully a virtual version. I mean, it might be possible to buy one or find some version of one and then see what they do. And I would imagine they're probably very easy to hack through. The web application firewalls 5 years ago and earlier were really, really pathetic, and you could totally just change the case of a letter or add a space in the middle of something and get through them. And I would imagine these are probably from that generation if they're the government standard. Anyway, it would be interesting to get hold of some and see what they do. Let's see if there's anything else exciting. Oh, there's a big lawsuit about the pump and dump of Bitcoin, which came out in the book by David Gerard a couple of years ago, but now it's actually come out in much more detail. And this, so Bitfinex and Tether, is how they pump up the price of Bitcoin. Tether is their fake so-called stable coin that is supposedly backed by a dollar, but the dollars aren't really there. And they buy Bitcoin with it every time Bitcoin falls to make it seem like the price is high when it isn't. And they got totally caught having no money in the Tether reserve and stealing what money there was and moving it somewhere else and lying about it. So they're actually going to get getting sued by a bunch of people, and maybe there'll be some punishment for them for doing that. But that's one of the main Bitcoin exchanges. And this is it Huawei? This is the main Chinese store, Baidu. Baidu owned this company, and they spun it off, and they still own 30% of it, and they're filling the Play Store with malware. And this, I think, is something I've seen from looking at the number 3 browser in the world is UC browser from China. And you just run it down and scan it for malware, it's all full of malware. It's the main browser people are using. And I think my impression of the Chinese internet system is it's like it was here in '98 when everybody's just infected and half the stuff you download is full of nasty adware and malware, and people just are used to it and don't expect things to be clean. That seems to be the way it is. So even the big reputable companies are handing out malware. Anyway, all right. So I think we can carry on with elliptic curve cryptography. So that should be here. There we go. All right. So the elliptic curves were pushed very heavily by the NSA and adopted everywhere because they save money. They save CPU, battery life, and money by giving you secure encryption with much less math. But the cost is the fundamental math underneath it is more complicated and confusing. So this was introduced in 1985. It is the newer improvement over the other public key systems. More efficient, more powerful, so you can have a 256-bit key, and that is stronger than a 4096-bit RSA key, which is a big improvement, because as we've seen, RSA involves these very painful activities like finding a prime number and even finding a safe prime number, and those are very expensive activities. But it was adopted pretty slowly. It came out in 85. It was 20 years before OpenSSL adopted it, even longer before OpenSSH adopted it. And this is the same thing we talked about many times. There's a new thing that's better, but nobody really cares as long as the old thing still works. Bitcoin uses it, and now a lot of protocols can use it, but not this thing called secure remote password, which I didn't know about. I went and looked it up. It's an interesting protocol to do something that's more or less like Diffie-Hellman. You can create a password at one end and have it at the other end and send something over the network that doesn't include the password. You can prove that you own a password without sending the password over the network with this system, which looks really very nice, but for some reason it can't use ECC. Anyway, so an elliptic curve is a very strange thing. It has nothing to do with an ellipse. It is the mathematical formula. It's kind of like the mathematical formula for an ellipse. Y squared equals x cubed plus ax plus b. So it looks like this. There are certain regions where there are no solution. There's certain values of x like 1 where there is no solution. And there are other values on the left where you have a positive and negative. In all cases, there's a positive and negative solution that are identical. So let me get this set so I can move my mouse around on it. All right. So it's always symmetric about the x-axis because this is an equation for y squared. So when you find a solution, there's a positive and a negative number that solve it because you only care about the square. So that's one thing that's always true. And here, these form a closed loop and these form a parabolic looking loop, and that's just it. It's just now this diagram is kind of pointless and serves only to confuse you as far as I can tell, because you don't use this to do the cryptography. This is the real number solution. And you don't use real numbers in cryptography. You use integers on a modulus. So the real one using cryptography looks like this. It just looks like garbage because, of course, you solve that equation and you get these huge numbers that roll around and wrap around. You put it modulus something, and so you just get essentially random numbers. But the point of this math is you can take a point, x, y, and you can map it to another point, x, y. And this is why you just have to understand this. The RSA was so easy to understand because it's just multiplying numbers and using a prime number, very simple stuff. But the fundamental operations are just group theory, and you have to think more abstractly. This is analogous to RSA once you get off using the specifics of it. So you have a field. Now a field is a group that has two operations, not one. A group, remember, has a thing that has elements and it has a way to combine the elements, which they call addition or multiplication. Field has both addition and multiplication. And both of them are groups. So you call that thing a field, and if there's a finite number of entries, you call it a finite field. And this I thought was interesting. I did physics and field theory for years to some extent without really knowing what a field was, because I wasn't that deeply into it. But anyway, so in order to have groups and a field to work on, you have to define these elements. You have elements are P and Q. Those are points on the elliptic, points that solve the elliptic equation, and you have some way to combine them. The operation, so we're going to call that this one. You draw a line between them and find the point where it intersects. So if I have a point P and a point Q, there has to be some way to combine them to create another point. And this is the way you do it. You draw the line, find the intersection, and then flip it across the y-axis. Now it can be any kind of operation you perform. The only rules are the operation has to take points that are in the group and end up at points that are still in the group. And there has to be an inverse and there has to be an identity. That's all you need. It doesn't have to be anything much like multiplication or addition that we're used to. It just has to be some way to take elements of a group and combine them to make another element of the group. So here's the inverse. There has to exist something called minus p, and in this case, minus p is just you flip the y value. It's the other one, the negative one. So because if you have, we can do that right back here. So if I have P, minus P is right down here, where you only flip by. So if you connect those 2 points to see what you get if you add P and minus P, you get a vertical line that goes off to infinity. It never cuts the curve again. It never hits it again. So there is no solution to P plus minus P. So you always get the same value. If you take any number in the group and add it to its negative, you'll get a straight up vertical line and it will go to infinity. So you always get the same answer every time you add P and minus P. And you can call that answer 0. I remember I heard about this like 40 years ago and I said, wait, how can you call infinity equals 0? You're making my brain hurt. But it doesn't have to be the kind of 0 we're used to. It just has to be the number you call 0. There's a special number you get when you add the negative and positive, and that's what serves the place as 0. This is like you take the same old math and you just have people put on masks. I'll pretend to be addition, you pretend to be 0, and all the math will go the same way because it doesn't matter what really happens. What matters is that you have little toys like checkers and you're flipping them around as long as they move in the right pattern. Because remember, all we want to do is feed in the plain text and shuffle it around to make ciphertext and then shuffle it back to get back to plain text. It doesn't really matter what the math is. We just have to have some kind of pattern of how we scramble it and how we unscramble it. And this is the mathematical description of just another way to scramble. And one thing that helps me remember is RC4. RC4 was nuts. You just shuffled the bytes like a deck of cards, and that's all you did. And that was enough to make encryption and decryption. It doesn't really have to contain normal operations you'd think about like multiplication and addition. It just has to be some pattern of how you scramble the bits and then how you unscramble them again. So that's the game here. This gets you to the point of infinity, and I call that 0. Yeah. Oh, I have a question. Oh, good. Yeah. Well, that's a good sign because this is kind of mind-boggling stuff. I understand in theory. In practice, how does an argument implement securely if its math is so complicated? Well, this is a very good question. And of course, the way you implement any of this stuff securely is you don't. You just get a standard library like TLS or OpenSSH. You just use it without touching it. That is the wisest move. Writing your own crypto is never recommended, and especially for this. So I mean, that is the right answer. Take something, choose whatever language you like Java or whatever you're using, Go or whatever you have, and go find a trusted library that implements it there, and then just learn how to use the library. That's what I would highly recommend. And it's a very good question. And the only reason to understand what's happening inside there is so that you can understand more clearly how to use the library, and you can understand what the defects and risks are. I certainly wouldn't write your own code to do this except as a learning exercise. I wouldn't use code you wrote yourself. So now that we've defined addition, and we now defined how to add 2 different points, and we've defined what a negative point is, now we're going to do multiplication. Now this is easy. If you multiply by k, you just add it together k times. So that'll do it. Now the addition is a whole lot harder than normal addition. You have to do this geometrical thing. So you might want to make it faster by calculating P2 and then adding 2 P2s to make P4. And that way you'll only have to do a logarithmic number of additions instead of for large values of k, because we're ultimately going to get up to like 256-bit numbers, which is a pretty big number. So we're not going to want to do 252 to the 256 operations, adding them. We'll do it this way. And so now, here's what a group is. This is a general thing from previous chapter. A group is when you have a set of elements like X, Y, and Z, and then you have 4 properties. You have elements, and you have some kind of operation that will combine them, which I'll use the X for. And closure is if you have 2 elements in the group and you run them through the operation, you get another element in the group. You don't create something that's outside the group. Associativity means you can do it in any order, X times Y times Z or X times Y times Z. Identity means there is somewhere an identity element, so that E times X is X, something that returns the same value when you combine it. And the inverse means for every X, there is an inverse, so X times Y equals E. And this helps with the problem with that pointed infinity nonsense. The pointed infinity is, well, anyway, it did nothing really special about 1 or 0 here. It just has to have this property. There's an identity element like 0. When you add 0, it stays the same. And there's an inverse where you combine 2 numbers, you get back to the identity element. So you can do also elliptic curves. P, Q, and R are curves. The addition is going to be that weird operation where you draw a line between the 2 points and find the intersection and flip it. And so now you got closure. If P and Q are in the group, the combination is also in the group because you were on the curve and you took an intersection with the curve, so you're still on one of the curves. The associativity holds, and there is an identity element, the point at infinity. If you add the point at infinity to anything, by the way, you can see that geometrically. So if I'm at P, and then if I'm at P, and I move Q up to infinity, then I have a vertical line, and the vertical line will turn P into minus P, and when I flip it around Y, it'll come back to P. So the point at infinity is the identity element. If you add, it's the zero element. If you add infinity to P, you get P. Yeah.
Is this defined like a private key between two parties? Like if I give you P and you have Q, and then now we know that our common factor is P plus Q?
Yes,
Okay.
exactly. You can do Diffie-Hellman with this because the logic is the same. It's just the symbols look a little funny and the underlying math is sort of mind-boggling, but if you just mechanically turn the crank on the same logic, it will work.
Okay, and then the hidden values here are the functions that give you the curves.
No, the curve is not hidden. The curve is not secret. In fact, everybody uses the same one. That's because only certain curves are good to do for this, and there's a few published ones. Everybody just agrees to use the same curve, just like everybody uses the same E in RSA. There are secret numbers, which we'll get to. You pick a random number to start with, but the curve itself is not a secret.
So P and Q couldn't necessarily they couldn't be public.
No, you corn P by multiplying two numbers, a secret key and a shared key. Yeah, you'll see there. Yeah, the P itself is not your secret key. The P is, your P, however, includes your secret key. It's just like Diffie-Hellman. You're right on track. All right, so anyway, so now we've got, so that's what the identity element is, the point at infinity, because if you add infinity to a number, you get back the same number. And the inverse is just where you flip the y-axis, and then those two numbers add together to form the zero, which is the identity element. So you can now define the fundamental hard problem, the digital logarithm problem. The EC digital logarithm problem goes like this. If you know P and Q, find K so that Q is K times P. This is division, and that turns out to be a very hard problem, just like it's analogous to the logarithm in Diffie-Hellman. This has turned out to be in practice very hard, and everyone has found a way to solve it quickly. So this is the fundamental hard problem you're based on, and this is where we're getting. That's why I say you'll have a secret key, K, you will multiply it something, and this will be your public key. And people who know your public key will not be able to find the secret key from it because this problem is hard. So this makes the numbers much smaller. So you use a field ZP where P is a prime number, and it turns out if you use a prime number n bits long, the security is n over 2 bits. So 256 bit prime number, which is the size of the modulus, will give you 128 bits of security, which is uncrackable in practice, and that's better than 4096 bits of RSA, which gives you 90 bits. So here's another question. In ECC fields, does the multiply operation also have closure, associativity, identity, and inversion? And I believe it does, but I have not worked through it. But I think that's why it's a field. I could be wrong, but my understanding of a field is that it has two operations, and both of those operations are groups. That's why a field is different than a group. A field is a more specific situation where you have these two operations, and each of those operations leads to groups. That's a very good question. You're right on track. All right. So here's how the Diffie-Hellman works. Now here's the old Diffie-Hellman we did before, the original Diffie-Hellman. You pick a random number A, and you have a public number everybody knows called G, and you just send G to the A. The other person puts random number B, and they send G to the B, and now each of you can deduce your public key. You calculate G to the AB. I take my private key times the other person's public key, and they both end up with the same number. One of them gets G to the AB, the other gets G to the BA, and because it's associative, we have the same number. So now we have agreed on a shared secret, and the numbers we have transmitted do not lead to the private key because of the discrete logarithm problem. It is a known hard problem that even if you know G to the A, you can't figure out A. That's how it works. And ECDH is just the same. I pick a random secret, which is G to the A, then I multiply it by G and send that over to the other end. This person takes a random secret, G to the B, and transmits that as their public key. We each combine those two numbers with the operation, which you could call multiplication, and here's the shared secret, d to the a times pb, which is the other person's public key, which is d to the a, d to the b times g in both cases. It's exactly analogous. We take the public information that was sent over the untrusted channel, multiply it by our secret in both cases, and we end up with the same shared secret. And again, just like before, the shared secret is not white. It is not equally likely to have every bit 0 or 1, so you should hash it before using it as a private key, but at least it is shared, and the stuff you transmitted over the network does not reveal the secret because of the elliptic curve discrete logarithm problem, which says that knowing the product of g times d to the a does not mean you can figure out d to the a. That's the elliptic curve discrete logarithm problem that is known to be hard. So it's just the same. And so now you can make signature protocols. So if you want to sign with it, there's a signature protocol for elliptic curves. This is therefore a lot faster. And so there's two algorithms, a signature generation and verification. And so the signer holds a private key. The verifiers hold the public key, which is that times a number. And now they both know what elliptic curve to use. You've all agreed on this. You know the order n, and you know the coordinates of a base point g. Those are all public information. And now you can sign it and people can verify it. You can sign it with your private key and people can verify it with your public key. So you hash the message with some hash function like SHA-256, and then the signer picks a random number and signs it and creates this thing R and S, which is twice as long as the key. They try combining a few numbers together and including their private key in here. K is their private key. That's their secret key. And so people can verify it with public information, but they can't reproduce the signature. It has the usual properties of a digital signature. And the signature length is 512 bits if you're using 256-bit keys, which is a whole lot smaller than RSA signatures, which are 4096 bits if you want reasonable security. So RSA is used only for encryption signatures. ECC has more opportunities. It's a more advanced protocol. Of course, it has more fancy stuff like key agreement and something called identity-based encryption, which is some kind of authenticated encryption option, which they don't go to in any more detail. But if you, I went to PasswordsCon, and they combined it with B-Sides Las Vegas a couple times, and it was really very interesting. They had these cryptographers show up and talk about all these mind-blowing new cryptographic things. The one that I thought was unbelievable was homomorphic encryption, where you can have a service like Dropbox, or you can have a database. You can have privacy that works like this. You put your private information in the database, they encrypt it so they can't read it, but they can still query it. Someone can query it, and you can tell if it's there or not. If the query person has like a private key, and you can tell if two of them are duplicate or not. It's very interesting. There's encryptions that gives you the ability to like search encrypted data without decrypting it and stuff like that. All of this stuff is so extremely complicated, it's too slow to use in practice. But these newer people are trying to solve these bizarre encryption problems and develop sophisticated protocols.
Similar to hashing values and values as well.
Yes, yeah, but it has new properties. Where the encrypted stuff still has some useful patterns in it, but it can't be decrypted. Anyway, all right, so it turns out the signature and verification algorithms are much simpler in RSA, easier to program, but and the verification process can be faster in RSA if you choose a small e, which is commonly the case. Of course, you pay for it by having a slower signing process. So the advantages of ECC are shorter signatures and the signing speed is faster. The verification procedure is not necessarily faster because RSA is typically slanted to make the verification easy and the signing hard. But here's the real results in the book about the signature. RSA of 4096, you can do 137 signatures per second, but elliptic curves can do 21,000 signatures per second. So it's 150 times faster to sign, and the verification was essentially the same with a 4096-bit key. So, you know, that's why people are pushing it. ECC saves you a lot of CPU time, and therefore a lot of battery life, and it saves you some network transmission time. The things you're storing are smaller. You know, it's a whole lot more efficient if you can, of course, write the code well enough to do this sort of weird mind-bending calculation. Now, if you were to try encrypting with the elliptic curve, remember, public key systems are actually pretty miserable at encrypting messages because they don't have a way of doing block after block. You only encrypt stuff up to one size of the key, and that's it. They're not intended for encrypting long messages. And in RSA, since your key is 4,096 bits long, you can encrypt up to around 4,000 bits, but in ECC, you only encrypt up to about 100 bits of message. So that's really pathetic. That's not even enough to encrypt a private key and send it. It's really hard to see what you're going to accomplish with encrypting something that small. So what people actually use, of course, is the integrated encryption scheme, which we're all used to. This is what TLS does. You use a Diffie-Hellman exchange to make a shared secret. This is the original one, using RSA, using prime numbers. Use Diffie-Hellman and make a shared secret. Then you hash the shared secret to make a symmetric key, and now you use a symmetric encryption like triple DES or AES with that secret. This way you can move as much data as you want, and it's relatively secure. If these things are strong, it's just as strong as the algorithm you use to make it. You can do that with elliptic curves. Pick a random number, compute this point, send that point over. This is, you make an ephemeral key pair, and now you create a shared secret, and you use a key derivation scheme to make a symmetric key from the secret, and then you encrypt it using a symmetric cipher like AES, and off you go. It's the same thing. You're just turning the crank on machines with different labels, with relabeled the components, but the same process goes through. So then you got the problem of choosing a curve. It turns out that you can't just choose any elliptic curve, because some of them have loops. Remember the Pollard's row function, where you try to go around all these values, but you get stuck in a little loop and it only explores a small number of values. And if that were to happen, then it wouldn't be secure, because then you could brute force things and reverse the logarithm problem. So you have to choose A and B. And it's not obvious what you should choose for A and B. The first thing is you have to make it so that the order is not the product of small numbers. So you often choose the prime number for the order to make sure of that. And it turns out that the early generations of ECC had a special problem when you add a number to itself. If you add a number to itself, I go way back to these silly diagrams. Okay, if I add P plus Q, I draw this line and make a tangent. But if I add P to itself, then it's not obvious how to do that. So the rule is you use a tangent line, but that means you have like an if statement in your programming. If P equals P, and you're adding P to P, do this other thing. So that might take a different amount of time. It might have certain consequences for certain kinds of data. So it turns out to be a poor security decision if you have a different algorithm for P plus P than you have for P plus Q. That's likely to be something that could be exploited to leak out information about the key. So it would be considered safer to have those two be the same. But you have to somehow find A and B, and this is the one that buries a lot of people at the NSA. If you're using the NSA's A and B and they won't tell you how they got it, you wonder if they got it in some horrible way that makes a backdoor in there. And that's the NIST curves. These are the standards from 2000. They gave us 15 curves to use, 5 prime curves, and 10 others using something called binary polynomials that are supposed to be faster, but nobody cares. Everybody uses the first 5. First 5 are the ones everyone uses, and they pretty much all use this one, P256. This is the standard everybody uses. And they call it 256. It's very obvious. You take a prime number that is very close to 2 to the 256, and you make this. It turns out you can make prime numbers by combining just a few bits. So all the bits in this number are 0 except for a couple, or actually they're all 1 except for a couple. But anyway, you can take just a few bits and create a very simple number here. That's the prime number you use. You put a 3 here, and the only missing number is B. There's a way to create an elliptic curve, and the problem is they will not tell you how they got B. That's where the rub is. They got B with the SHA-1 of this number, but they won't tell you how they got that number, and everyone is worried, a lot of people are worried, that they mysteriously have created this number from another number, and knowledge of that number means they can predict the results of encrypting with this curve. And some Microsoft researchers, mathematicians, 10 or 15 years ago, proved that that was in fact possible. It is possible to carefully choose this number from another secret number, and then you can crack the encryption. And so they suspect that the NSA did that. That's why no one has proven there is a backdoor, but they have made an argument that there could be a backdoor, and you would never know. So some people don't want to use it. So this is the standard that almost everybody uses, P256. From the NSA. Of course, anybody that does real business with the military or the government, they don't really care if the NSA is snooping on it. They just want to obey the standard to get their business. And that's what most people do. However, the people that are not willing to play along with the standard use this one, curve 25519. And I wondered what this number was until I see it. You'll see this is just the numbers that were used to create it. So this one is a more modern one. It's considered more secure. It has this desirable property that exactly the same algorithm is used for P plus Q and P plus P, which the earlier ones do not. And here's the point. It's 2 to the 255 minus 19, which is not a number that they pulled out of a hat. That is the prime number that is closest to 2 to the 255. That's it. And that'd be easy enough to verify. So that's a number that is clearly not poisoned. Then he calculated this number, and that's why it's called 25519. It's P is 2 to the 255 minus 19. So there you go. This is the one everybody uses. Chrome, Apple, OpenSSH. It's not the standard. So anybody that's willing to be non-standard uses this one. It is the de facto standard for the rebels who don't trust their government, because there could be any nasty people like that. So there are others. Yeah.
So Microsoft just switched over to using the Chrome engine. And I know Microsoft has a lot of ties with like...
But they're not using the Chrome engine. They're using WebKit.
Oh, no, I know. They're using the Chromium.
But I thought they were just using WebKit, but I'm not sure.
Yeah.
That's interesting. So I wonder if they are still, because Microsoft is very much into using official military and government standards. So I don't know. That's a good question. I do not know the answer. I would imagine, though, that Microsoft probably switched to use standard protocols, because they usually do. Let's see. Might have missed this. Did the NIST curves use different algorithms? I think they did. The original NIST curves were old, and they did use different algorithms for P plus Q and P plus P. And that's why the later algorithms fixed that. That was a possible defect, although I'm not aware of any real attack based on that, but there might be one. But anyway, so this is the new Rebel standard. There are others. France and Germany have their own version of this standard, which they also don't explain where they got numbers from, and various people suspect that their spy agencies poisoned them. So nobody much is jumping on them, but some people are using them in those countries. And there are newer ones. 41417 is an even more secure version based like the 2551, and there's something called ED 448 Goldilocks, and these are intended to be the more secure versions, which are longer than 256 bits. All right, so but almost nobody has moved up to them yet, but that is an option. I know that was the NSA's official recommendation, which we covered way back at the start of this class, was that they're worried about quantum computers, and they're afraid that quantum computers are going to break this one, 256, and they say we should be using 384 bits instead, just like we should be using 4096 or 8192 bits for RSA, because they're worried about what quantum computers will do. And that is not going to save us from real quantum computers, but it will hopefully save us for a couple of decades while the quantum computers are still improving. And when the quantum computers really start working, we'll have to ditch all of these and switch to lattice encryption or something. So, all right, so that's where we're at. And here's a couple of attacks. The elliptic curves have more parameters, and they're more complicated. So you're more likely to make a mistake handling something. And if you're handling all those large numbers, there might be side channel attacks that have to do with timing, how long it takes to do the calculation. So that's one issue. You can have bad randomness. This happened to the PlayStation, 2010. If you reuse the same secret key twice, then the whole thing shatters like glass, which you may remember was also true of the one-time pad. You got that in your homework. If you use the same one-time pad twice, it's shot. And the same thing is true here. If you use the same secret key twice, then you can just take the encrypted stuff, the public information, you can derive the key from it and totally break the thing. So this happened to the PlayStation. And the Chaos Communication Congress had a presentation for someone who hacked into the PlayStation this way. And this one, I had to do a lot of Googling and reading papers to get this straight. I finally understood this invalid curve attack. It turns out in HTTPS, in TLS, you propose a parameter to the server, and the server agrees to it. You can maliciously choose an evil K, which causes it to be in a short loop, like a total of 5 values. So when the server thinks it's encrypting securely, it's not, and you can find their private key. That's bloody awesome. The client can give you a malicious public key, which is derived from a carefully chosen private key, which causes the server to encrypt insecurely, and the server doesn't know this has happened. And it thinks this stuff is securely encrypted, and you can leak out the server's public key. So it ends up being like Heartbleed, where you can steal the secret keys off the server. So that's bloody awesome. And this was in 2015, and it hit a real library in 2017. So this is pretty cool stuff. Now, there is a patch of some sort, which I haven't read how it works, but I imagine it somehow detects whether you're using one of these malicious numbers. Yeah.
Well, the book mentions the importance of validating the input, and that will prevent
Yeah, but you have to somehow know what malicious input. Somehow there is some way to detect malicious input. And that's, anyway, it's a pretty cute idea. And anyway, this really happened. So this is why, I must say I have sympathy for all the people who didn't jump on this, because banks especially are good at this. So you have some new idea, it sounds great. Yeah, call me in 20 years. After other people have used it for 20 years and we see if it really works. Because it might sound good, but there might be a hole in it. And here's a hole that you wouldn't have happened to you if you used RSA. So, I think a lot of people are wise to just keep using the existing system you can trust and not jump on the new thing until everyone's hammered at it for a good long time. Anyway, I got some cahoots about this stuff. I've got them open even. Life is good. I should even have a place to put the cahoots. I do, okay. All right, how many have we got? Oh, 10 people online. Well, there might be more cahoots coming in then. This sounds like low resolution MIDI music. Every note has this. Play what?
Canyon.mid.
I don't know that one.
You don't know Canyon?
I know.
It's like it's Microsoft Windows with the 90s Thomas.
That sounds good. I know the game with the blocks. That used to have great MIDI.
Oh, yeah.
Hungarian Rhapsodies or something. All right. Well, I guess I'll wait a few more seconds and go. Ah, there are more cahooters coming. Okay. All right. I'm giving it another 5 seconds. Ah, there's M-Dot, the winner from the purple team. All right. Good. All right. All right. So how long should your ECC key be? There's a practical question. That's your 256. That's the point of it. That's strong enough, 256. All right. How long a message can you encrypt with AES? Any length, of course. It's a symmetric key cipher. You have blocks. You stick them together with cipher block chaining or whatever you like. You can go as long as you want. Which one is the curves that some people think the NSA backdoored? That's P256. By the way, the textbook author poo-poos this. He says, oh, it's not backdoored. Most people agree it's not backdoored, which is news to me. So maybe it's one of those things where the actual experts know it didn't happen. It's just sort of the fluffy hangers-on that don't understand the stuff that think it's happened. I really don't know. Anyway. All right, so how long a message can you encrypt with ECIES? Any length. This is the integrated encryption scheme, which lets you, again, lets you use the ECC to create a shared secret and then hash it and use it. That's the IES, the integrated encryption scheme. EC by itself could only do 100 bits, but this is the integrated encryption scheme where you combine symmetric and asymmetric ciphers to create to encrypt a message of any length. All right, so here are the winners. Aha, M-Dot again, good. Caitlin. Right, I can't type anything. And oh, we'll have to tell me who they are if they want their points. Is that you? Not you. Okay, well, then they're going to have to give me a clue if they want their points. That's not enough bits of information. All right, so I'll wait a few seconds to see if there are any questions or information coming in. I see a Q. A cat message has already come in. Okay, good. Now I know who Q is. Good. Thank you. Good. All right. And I guess I'll knock it off. go upstairs and see if anybody wants help on anything. Farewell.